Hello everyone, welcome to this EAGE lecture. My name is Rietveld and I work for BP as Seismic Delivery Manager for the North Sea region. In a previous role for BP, I worked as Senior Seismic Processor in Egypt, and the work that I did there is part of this presentation. The presentation is entitled Multi-Azimuth Streamer Seismic in the Nile Delta, and this part is part 2 around depth imaging, which does suggest that there's a part 1 as well, which hopefully you've already looked at. Part 1 was mainly about the reason why we did multi-azimuth seismic and around the simple time processing and time imaging. In this presentation I will actually focus on building a depth model and the depth imaging. This work was presented previously at an EAGE workshop, and the reference is here. If you're interested in this subject and would like to read more, I suggest that you look up papers by the authors here, Ted Manning and Dale Baptiste, and that should give you a good opportunity to get a bit more background information. So the outline of this talk is that I'll first introduce the seismic challenges in the Nile Delta to you. I'll quickly go through the solutions, which will be multi-azimuth seismic. I'll very briefly summarize some of the results from the time imaging, and then I'll go into the depth imaging story, which is mainly focused around the model building using tomography. I'll also talk a bit about parameterization, and then we'll look at the results and some conclusions as well. So where are we? We're in the Nile Delta, so you see the Mediterranean here. You can see Cairo indicated with the Nile Delta to the north of that, and we're just offshore there. And we're mainly in the West Nile Delta looking at data from the Raven field. Raven is part of BP's development in the West Nile Delta there. So if we look at the issues with seismic in the Western Nile Delta, here we look at a regional line. You can basically see a dipping water bottom going away from the coast, and you can see the Messinian layer sitting there in the middle as indicated. The Messinian layer was deposited a couple of million years ago when the Mediterranean dried up, and it's basically a conglomerate of all sorts of different lithologies. You'll find there salts, you'll find sands and shales, and you can also see already from this image here that it's highly variable as well. Now the combination of that Messinian layer and the water bottom, and especially also the quite small scale diffractors that sit right below the water bottom, set up a very complex multiple sequence, which you can see indicated on the left hand side. What you can also see is, if you look at the Messinian and the deeper section here, is that if we actually do a PowerPoint interpretation of the Messinian, you can see these spots there. And below these spots you can see that in some places you get a pull up, so you can see that the events below it are pulled up, and then in other places you can see amplitude distortions. These are things that really require depth imaging to solve. For depth imaging to solve that, you need to get a very detailed model of the Messinian, and also of course of the overburden above that, to be able to basically get a perfect image in the pre-Messinian, which is where the Raven field actually sits. So the seismic issues in the Nile Delta, just to summarize, so we've seen very complex multiples, velocity model complexity, which is specifically the thing that we're going to be looking at in this presentation, and just general noise levels as well. So what is multi-azimuth seismic? It's basically your bog standard towed streamer seismic, but then you acquire it in different directions. So here we've indicated that actually for Raven we acquired 6 azimuths in total, but you can also do 2, 3, whatever you like. The thing is that if you do less than 6, or however many you do, that they're as diverse as possible. And the reason why you do that is that by shooting more seismic in different directions, you'll start figuring out a way to possibly undershoot some of these smaller scale anomalies that we look at. So you should get better illumination. The fault and azimuth diversity should give you better noise suppression and a better suppression of the diffracted multiples. And the fact that you actually got better sampling, you got more data going in, you have a larger antenna and therefore also a better spatial resolution. And it works. So this is basically an image that I should have shown in part 1, but I saved it for part 2. On the left hand side you get a single azimuth amplitude extraction, and on the right hand side the multi-azimuth, so 6 azimuths put together. This is quite deep in the section, and you can see a distinct difference in sort of the geologic features that you can identify. The meandering channel on the right hand side, you can actually see individual meanders going through, whereas on the left hand side you can just see hints of the fact that there's a channel system there. The darker blue lines that you can see quite clearly on the right hand side are faults. They're very clearly imaged, showing you better resolution, whereas on the left hand side you can identify them sometimes, but they're not half as clear as you can see on the right hand side. This is after a standard processing flow, including time imaging, and then a bunch of trim statics to basically get data to line up. If you want to know more about how that went, take a look at part 1 of this presentation. And if we look at diffracted multiples here, just a quick sort of image again. On the left hand side, one azimuth, right hand side multi-azimuth, you can see that the noise is suppressed quite effectively, basically showing that multi-azimuth actually works in that sense. But if you look at it, you can still see that there's issues there. So you can see down deep, if you go from right to left, you can see on the right hand side quite good continuity of the event, but when the Messinian becomes more complex, you can see that there's holes there that are not well imaged. And it's not just down deep, but actually up shallow, you can see the impact of that very shallow, likely gas chart channel sitting there that causes an amplitude dimming right below it. Now to solve this, in a depth imaging sense, it's not just solving for the Messinian layer itself, but you also need to be able to resolve that shallow gas charged channel there to be able to actually get a good image out of this. So we've looked at tomography in the Nile Delta before and depth imaging, but we never managed to use single azimuth data to actually resolve the issues that we need to resolve. So the question is whether multi-azimuth seismic can help take into account that very shallow low velocity channel, and they're really all over the place in the Nile Delta, and then also take care of the strong lateral velocity contrast in the Messinian itself. And there is some historic evidence. Now remember that we presented this in 2009. So in 2008 there was some work by Tennis who showed that on these seismic images you could do an inversion and then take the impedance data, do some thresholding there, and that way actually start building sort of a very detailed model of the anhydrite distribution in the Messinian layer. That was only partly successful, but it did show that there's actually information there that we can use to try to go after building an accurate velocity model. And at that time also Western GECO had been showing some results from dual azimuth tomography, so using multiple data sets to basically improve their velocity model building. So all these things are pointing that there should be a depth imaging solution using multi-azimuth seismic. So the model building flow that we've used, basically the top 2 sort of red boxes are your box standard sort of single azimuth tomography and velocity model building that you would do on any sort of project. The multi-azimuth aspects really come into play for the MAZ iterations 1, 2 and 3, where we basically start from shallow with a relatively coarse grid, so 100 by 100 meters in terms of the model itself. And then as we go deeper, we go from single parameter to multi-parameter, tighter grids, and then we go deeper and deeper. And especially the last iteration, we applied a bunch of stuff to try to basically get better quality picks in very challenging areas. So we had harsher noise attenuation, we tried to build better automatic picking, we used more horizons, I'll come to that later, and then we tried to basically let the data speak. So try to damp the system when you run the inversion as little as possible, so that you actually could get the data tell you where the anomalies should be. And then there's some smart smoothing in there as well in terms of the residuals. We'll come to all these points as we go through the presentation. Now, the thing to note is that at no point in this model build is the model frozen at any level. So every iteration, we basically pick events from top to bottom at every level that we can. And then we let the tomography decide whether actually some of the new sort of anomalies that he sees down there are actually caused by a little change up shallow. So every time we try to basically update the whole model. And the reason why we do that is because in that way you avoid sort of cumulative errors actually starting to come up right at the bottom of where, at the level where you've frozen your model. So we've left that open, and then we basically pick residuals everywhere at all depth. So a lot of words, let's see what actually happened here. So first of all, the way that we actually do the analysis is that we pick residuals along horizons. So we basically take our seismic and we pick horizons on them, and then along those horizons we basically pick move out. So, and in this case it's second order move out, it's a single parameter therefore, but we do use multi-azimuth tomography for the update. So in the top right corner what you see are basically slabs of semblance. So each slab represents the semblance of a single surface. And that's what you would pick. And then you go to the next surface. And you do that for all 6 azimuths. The maps on the bottom right hand side basically show you for the different azimuths sort of the results that you get from this single parameter pick. So all that information for all these surfaces, and you can take as many as you can, will then use to basically update the model up to the Messinian layer. So if we look at the result of the tomography, we basically see on the left hand side the velocity model by itself, and on the right hand side basically blended in with the seismic. You can see that there are some long wavelength anomalies that have already been identified. You can see the very shallow channel already giving sort of a bit of an imprint on the velocities, very shallow to the water bottom. And you can see some of the bigger pots in the Messinian. You can see actually the velocity already starting to be pulled up. So actually indicating that we should have faster velocities there. But by no means does this model actually have sufficient detail in it that we can say that we've solved the problem. That's of course why we iterate. So on to the next iteration, where we actually go from single parameter to multi-parameter picking, which actually means is we're going to pick time shifts in each offset class. So in this case 28 offset class we're going to be picking them on, and for every surface. So if you imagine that in the first iteration maybe we used 10 or 20 surfaces, now we got 28 times more surfaces that we're going to be picking. So the amount of data that we have to go through, that we have to QC, really starts growing quite dramatically. Now the reason why we go for this non-hyperbolic move out is because the smaller scale anomalies basically don't fit within the effective wavelength of the spread, which means that you don't get just hyperbolic move out, but you really need to start picking the events and the subtleties in there to be able to start mapping that information back and putting these small scale anomalies in. So what we see here at the bottom right hand is actually a time shift for a single offset class. Now the fact that we're looking at a single offset class also brings in an additional issue, which is the signal to noise ratio in the data in general. That's one of the things that, especially when we start picking deeper, becomes a bigger issue, and that's something that we really try to tackle in sort of the third tomography when we get to that. So here we do multi-azimuth, multi-parameter tomographic update. And once we've done that, we hope to see the effect from that. So here we have the results from the first iteration, and then as I go to the next one, you can see the effect of this multi-parameter, multi-azimuth update. So if I just go quickly back to iteration 1 to iteration 2, you can see that now the very shallow gas charge channel, the very low velocities there really jump out at you, and it aligns actually very nicely with the seismic as well. You can also see, even though we haven't really updated very deep yet, is that also the resolution at the Messinian level is really improved. And right in the middle of the image that you're looking at right now, you can see that the higher velocities in that one big pot of Messinian layer there is really start jumping out. And also further to the left hand side, you can see that happening as well. We haven't really tackled the very deep section yet, because we haven't really gone there. But you can only go there once you've actually resolved some of the issues up shallow. And we're slowly making our way to be able to do that. So this looks good, but it still isn't good enough. So you go on to the next iteration. Now the objective is really now to try to update velocities down to 4 kilometers, which is really well below the Messinian. And we've really taken a different approach here. And the reason is that the noise levels in the pre-Messinian, when you start picking on single offset classes, is just not good enough to get reliable picks. So you have to get smart. The other thing is that we really need to, when we try to tease out more detail in the model, the sampling of the model itself needs to be smaller. So where initially we looked at 100 by 100 meters, and in the second iteration 75 by 75, we're now going to 50 by 50, and actually vertically we're looking at cells of 5 meters. And then we need to improve the quality of the picks for the tomography. The only way that you can build a model to improve a very bad data area is by actually get reliable picks in that bad area. And therefore we need to improve the signal to noise ratio. So we work on the noise attenuation and also the QC of the picks as well. So this is what the noise attenuation is buying us. And on the right hand side you can see some of the things that we did there, FX decon, and also complex wavelet transform to knock out some of the noise. And you can see going from the raw image on the left hand side to the noise suppressed, noise attenuated image on the right hand side, that we've cleaned up the data quite considerably. The quality of the pics, as you can see at the bottom, are still not fantastic on the right-hand side, but they are really a lot better than we see on the left-hand side. And because they are a lot better, it also means that our update of the model should actually result in a better model as well. So the improved signal-to-noise ratio below the Messinian is really resulting in more reliable pics. Now, this next slide is actually quite complicated, but it shows sort of the QC that you have to do to make sure that what you're picking is actually the event that you want to pick. So if we look all the way on the left-hand side, we basically see sort of the gathers for 3 individual surfaces. The stack in the middle, where you see all the surfaces, you can basically see how dense we actually sample the section. It's almost a full volume where we're actually picking at. Now with that number of surfaces and the number of offsets that we're looking at, we're actually QCing, what does it say, 6,720 maps in total of data that we need to check and make sure that actually the data in there is good. Because if the pics aren't good, our update is not going to be any good. Now what we did to actually try to stabilize some of the picking is that after we've picked the individual offset classes, we actually went for a higher order polynomial fit of those residuals for each location. And then the coefficients of those polynomial functions were then actually smoothed appropriately in trying to actually knock down the noise even further and actually get more pics also in the bad areas. So all these things were used to try to get as many pics of as good a quality in some of the challenging areas that we had. So once you do that, you get results as I'm about to show you now. So this again is where we started off from. So the first iteration, this was the second iteration where we already started to show a lot more detail, definitely up shallow, but also around the Messinian layer. And now we really hope to get a lot of improvements in that Messinian layer as well. And that's what we see here. So what you see happening, if I go back to iteration 2 and then move forward to iteration 3 again, is that there's less vertical blurring of some of the velocities. So when you look at that pot of Messinian right in the middle of that image, you can see that it's a lot tighter now. It's a lot more constrained without doing anything in terms of picking tops and bases and making sure that it stays in there. Just by having the dense picks over that whole interval, we're actually able to really get better control on the vertical resolution in that area as well. Interestingly, if you go to the left-hand side, where we have a very thick sort of Messinian sitting there, you can actually now start seeing velocity variations within the Messinian itself. So a lot higher velocities in the bottom part of the Messinian and slightly slower velocities up there. So now we're really starting to feel confident that what we're seeing here is truly sort of the heterogeneity that we expect to see in the Messinian, and that we're getting really a lot better at that. So if we look at the gathers that actually that we have produced now, I'm now going to compare the gathers from the initial model with the gathers that we get after iteration 2. And what we're looking at here are multi-azimuth gathers. So we have offsets increasing from left to right, and then within each offset class we have 6 azimuth there. So you basically have sort of the azimuthal ripple that you can see quite clearly on the long offsets. If we then go to what those look like after iteration 2, you can see that definitely on the near offsets the azimuthal ripple has largely been taken care of. So even though some people could claim or have thought that maybe that azimuthal variation is due to azimuthal anisotropy, which is probably there as well, the first order effect to take care of is actually making sure that the small scale velocity anomalies have been taken care of. And that already takes care of a lot of this azimuthal jitter that sits there. And we can really see that we've improved the model. It's by far not perfect, but it's a lot better than where we were. And definitely that first sort of 3-4 kilometer of offsets is actually looking pretty good. Now we're going to look at some details in the velocity model. So I got a couple of these slides where on the left hand side we basically have a slice through the velocity model with a color map which is indicated sort of at the bottom in the middle, and then on the right hand side we have the seismic section with the velocity model in the background as well, which actually has a different color map, just so that you cannot really compare those colors one to one. So here we see a very shallow sort of slice. And you can see the impact of lower velocities of that channel system sitting right there in the middle with a little bit of white in there as well. Now the area is indicating an area where you can just get a hint of a very sort of thin cut going through the velocity model. And that's actually something that's about 150-200 meters width. So we really have a lot of sort of resolution there. Now as I go forward, we're actually going to look at sort of the seismic slice now along the same thing. And you can actually see that a lot of the details that we see in the velocity model actually do correspond with sort of details that we can see in the seismic. So it basically means that the features that we see in the velocity model, even though still far less resolution than what the seismic is showing you, are actually geologically consistent, and that's really what we're after. So if we go to a deeper horizon, and now we're cutting through the Messinian, you can see that now we can see velocity variation along the Messinian, some faster and some slower areas. And if I go forward to the seismic, you can see that some of these areas actually do line up with brighter amplitudes, or actually very opaque seismic character. So here, for instance, right in the middle, you see a very sort of clear, clean blob. And if we go forward to the seismic, you see that it actually corresponds with more reflectivity in the Messinian. So again, a geologic consistency between the reflectivity that we see on the seismic and the velocities that we've derived from that seismic. And then if we go and just compare sort of the time image, which already was not too bad, with a depth image, you can really see that by building a detailed velocity model and going through all the efforts that I've just demonstrated to you, you do get an uplift in the general sort of data quality, and especially the sort of gross overall structure is imaged a lot more reliable. Are we completely there? No, we're not. We've only so far updated everything down to about 4 kilometers, and to really get better at the deeper section, we probably need to include a couple of more iterations as well. But overall, we have demonstrated that by actually putting the effort in, we can get depth imaging to work by utilizing the multi-azimuth data and by really getting as much information out of the data as possible to drive the details in our velocity model. So the challenges that we had: diffracted multiples, lack of illumination, and velocity complexity. Diffracted multiples and lack of illumination are really taken care of by the acquisition side. And in this presentation, I've also shown that the velocity complexities we can also deal with multi-azimuth seismic by doing multi-azimuth tomography and really driving down the information in that model as much as possible to get those details out. So in conclusion, we've demonstrated that we've successfully built a detailed velocity model in depth. Now we do have to realize that some of the limitations that we run into are due to the tomography and the ray tracer there, so that does limit the resolution. But we have shown by supplying it with sufficient pics of sufficient quality and really squeezing the last drop out of your tomographic inversion engine, you can actually really get details in your model. And that really talks about sort of that point there. Let the data speak. So constraints should help you avoid the null space, so you don't want to go off into Never Never Land, but you do not want those constraints to limit the resolution in your model. And the MAZ data was really essential to be able to do this. Together with that, the conditioning of the residuals in the poor data zones by knocking the noise down and making sure that we get reliable pics there was also very important. Because if you have somewhere no pics, you're not going to get any model updates there either. So there's obviously still a lot of more work that went into this. Another update to basically get the deeper velocity model working, because we've really not shown in this presentation the results from that. Another thing which since 2009 has definitely moved a lot forward is full waveform inversion. That should work really well on the shallow anomalies, and it might even, depending on your acquisition geometry, it could even work as far down as the Messinian. Now some experiments have been done. One of the issues that you run into when you try to link full waveform inversion with tomography is that the resolution of the models that they build can be quite difficult, or quite different I should say, which means that it's quite difficult to start merging the models together. So even if you would start with a full waveform inversion and get a very detailed model up shallow, by the time you then need to start running tomography, because the limits of your ray tracer in that tomography, you might actually have to smooth that quite heavily. And that's still something that you need to look at. But it's definitely a way of getting a very good initial model. But ultimately for the deeper part, you would always need to go to a tomographic update anyway. We also, at that point in time, thought about wave equation tomography. That's still something that hasn't really taken off very much. But we do believe that if you can get that to work, especially around the Messinian layer. That might actually be another way of improving the resolution of your velocities in that Messinian layer. So just to finalize, I want to acknowledge sort of BP Egypt, our partner at Raven, RWE Dea and EAGE for permission to publish this paper, and I would like to thank you for your attention.